not coming to the fluid part, or coming a little bit, or something, not really sure. I just wanted to mention the connection that's in my mind about these things, and just to sort of, in the early 90s, I didn't know that this 3D fluids were kind of an intractable, well-known problem in PDEs. And tried to find out, not to solve it, of course, but just to find out why it was hard. And I kind of found out why it was hard. And then decided to try to work on it anyway, but by using things that I knew. So at the same time, there was a lot of interest in quantum field theory, and there was some there's definitely a relationship between the difficulties in the two fields and of an analytic sort. So that, in fact, there's going to be some analysis coming up later, but all these things, all this analysis doesn't seem to really work too well yet. So then the idea was to try to use algebra or something else I knew, and then in the physics theory, there's this idea of an effective theory where they had an interesting formalism for having a lot of degrees of freedom in a theory, and then they sort of integrate out some of the degrees of freedom. The way they integrated was to find the path integral, which has a graphical formalism. And so the idea was maybe you could build effective theories with fluids using some of these similar ideas. Now the graphical formalism turns out, at least the tree part of it, is exactly what goes on in Stashiev's theory of the perturbation level, where you take an infinity structure on one chain complex and move it to a smaller chain complex. So infinity algebras, perhaps jazzed up to include non-trees, might be useful for building effective theories. So all the stuff that's been happening before, all these infinity algebras, is a possibility to use to build different algebraic models for fluids or other PDE problems. So in my mind, there's a definite connection. You take a complicated problem and maybe you make an effective theory using these techniques, quite deep techniques in algebraic topology called infinity algebras. So that's gives you kind of connection to the first two parts.
So now we are motivated to move on with fluids. This rough geometry part of the conference, and so the first speaker will be Shnirelman, so he will start with minicles and fluid dynamics without algebra probably. So you will see.
Thank you. So first of all, I'm very glad to be here and to see Dennis and all of you. For me, it was really great time when we were discussing with Dennis many years ago these problems in Brook. My idea is to tell something about the fluids, that little which I know. But I am from different background, in part even engineering. So maybe my worldview is quite different from of others here, but maybe it will give some useful mix. So let me start from the beginning, from the notion of the fluid. So we consider some, domain M, Rn, no compact domain with regular boundary, and consider the fluid moving inside this domain. So what is the fluid? Fluid consists of a continuum of fluid particles. So position of the fluid is given by position of all its particles, and the change of position is some permutation of this fluid particle. So the set of configuration of the fluid is some set of permutations of this continuum of the fluid particles. So in the classical fluid dynamics, the configuration set or space diffeomorphisms group now let's call D of M. Group of all diffeomorphisms of our domain M preserving volume, preserve the element of volume. No, classically these are smooth diffeomorphism or some prescribed regularity which can be specified. Now this kinematics of the fluid is the same as the kinematics of a group of diffeomorphisms. Now what about dynamics of the fluid? Naturally, element of group of diffeomorphism F in D from M to M. But M is in Rn, so M to Rn. And we can consider these maps in a wider space. So D can be embedded in L2 from M to Rn. Yes? No, this is a physical space because here the square of the norm of the vector is the velocity vector, velocity field, and the square of the vector divided by 2 is the kinetic energy. So we consider the metric on the group D as induced metric on the group of diffeomorphisms. Namely, if we have F T is trajectory in D, then the energy is 1/2 integral over M Ft dot square dx. It's kinetic energy. Now this kinetic, this gives us a metric on the group. Now formally this is an infinite dimensional Lie group and Riemannian manifold, and the main property of this group is that of this metric is that the metric is right invariant. This means that if we have G in D, then norm F G dot equal norm F dot. So we have these right shifts. Now, at least formally, this is some manifold V, some manifold in L2. So the motion along the manifold in a Hilbert space is defined by the Lambert law. Principle. It is this trajectory Ft double dot acceleration is belongs to T Ft V orthogonal complement of. So the acceleration is orthogonal to the manifold, to the constraint. so how to write it down in the form of some equations? The tangent space such that the set, the tangent space consists of incompressible vector field with the divergence 0, and if we have a boundary normal component, normal velocity is 0. So it is there. And using the Hodge-Well decomposition, we have that TFD equals the set of gradient P. So the gradient vector fields are orthogonal in L2 to these fields. And so the Euler equation, Lagrange Euler equation, looks as follows. Ft double dot plus grad T Ft is 0. And the kinematic equation Ft belongs to D. This means that it is for any T, it is a volume preserved diffeomorphism, and that's it. So these are Lagrange Euler equations. Now, before I discuss this equation, these equations, we can have some implications of the fact that the fluid is homogeneous. Homogeneous? Yes, please.
Oh, just to confuse me. So the delta, the gradient of P is just a projection of Ft dot onto the perpendicular.
Yeah. Gradient P orthogonals are gradients of scalar functions. Yes, tangents are incompressible vector fields. Yes, and this is an implicit equation. This means that F double dot acceleration is orthogonal, so it is a gradient of some P. Yes, P itself should be found from these equations. So, no, it should be, there exists P such that. Yeah, and it turns out that these two equations are enough to find P, given initial condition. So initial condition is F0 is, say, ID, F0 dot equals U0, initial velocity field.
So the word you said before is the thing has to move to stay on the body conserved.
Yes.
It accelerates in such a way that the velocity stays body conserved. That's the equation.
Velocity is tangent, and acceleration is orthogonal.
Right.
Yeah, this is the equation. So this is a general, the Lambert Principle, which in its turn is a consequence of the Hamiltonian principle, which is taken from nothing. This is, no, it can be explained in simpler words as acceleration of any piece of fluid is the sum of all forces which acting on it, and from some fuzzy consideration they say that the only force which acts between the neighboring fluid particles is the gradient of pressure. Yeah, but it is a circle because we have to give some definition of the fluid. The best of all to take it as a definition.
Right.
Best of all, what is the fluid? We have to define some fluid, give its constituent equation. So let's take it as a definition. So the fluid is the motion along the manifold D.
Can you write down the action that leads to these
Action, yes. Okay. Action. Integral from 0 to t, integral over m, 1/2 ft dot of x square dx dt. This is the action.
So does this mean it's a geodesic?
Excuse me?
So this is the geodesic equation?
Geodesic. Yes.
Yes, the geodesic equation for this action.
Yeah.
Yeah.
Could you tell us where the function p is defined? Where is the function p defined?
P is defined in the domain M.
So why isn't it in the action?
Why is it the action?
I don't see P in the action.
P does not appear in the action.
So
It's a Lagrange.
P is, if you wish, P is a Lagrange factor. Lagrange multiplier.
It's a constraint.
Can I say something? When I think about this, I hate this P. So in your Euclidean space, so tell me this is right. You're in Euclidean space, you have the velocity field at a given moment. So first, let all the particles run straight along geodesics with this speed given at a point. And to first order, that'll be volume preserving because the vector field dispersion is free. But the second order, it won't. So that second order term that distorts the volume is what you have to make the acceleration. That's a sort of, is that correct?
Yes.
That's,
Yeah.
Make it
So
preserve volume to second order.
if the particle move without constraint, their trajectories would intersect.
Right.
Yes, and P prevents them from intersection.
By making it volume preserving the higher order.
Yes.
Right.
However, you are right in your attitude because in any serious discussion, P does not appear. So we can eliminate P from this equation, and it is really done, and it's most useful. So I think I will never use it, this lecture. Yeah. Okay, next is the symmetry of this equation. As I say, the transformation f goes to f times g, which is rg. Right shift is isometry. No, plainly speaking, this transformation is just permutation of fluid particles. Yes, but because the fluid is homogeneous, this does not change anything. We simply rename the fluid particles.
But what is dx? Is that you fix some matrix on M?
It's just Euclidean matrix. We can do it on the Riemannian manifold, of course. But Riemannian manifold can be embedded in the Euclidean space. Yeah? So it is in fact no extension. Yeah? So I prefer to keep to Euclidean space or maybe to the torus. Yes, it is not the source of interest. The interesting things happen in the flat space and the depth of the fluid, so it's there. And so it is isometry. So now consider one parametric group of isometry with x is say W, generator. Of isometry. Yes, so x is tangent tangent vector field on the group D. Yes. Then we have the classical Symmetry theorem. Which says the following. So if we have a solution of these equations or a geodesic on D, Ft geodesic, then the scalar product Ft dot x at the point Ft is constant. What it is in our case? In our case, it means exactly the following. Suppose we have this W is generator, it's an incompressible vector field, and then we have integral Ft dot of x times Ft prime of x times W x. The x is constant. Integral over x. Yeah. So the vector field W is transported, pushed forward by the flow, and its scalar product is yes. No, what does it mean? In particular, it means the following thing. We can consider the vector field W, which is concentrated in a thin tube. Yeah? And in the limit, this goes to vector field, which is delta concentrated on a contour gamma. And then this means the following. Integral over Ft of gamma u ds is constant, where what is u? U of y Ft dot Ft minus 1 of y. So it is a velocity field of the fluid. So this means that if a contour is moved by the fluid, then circulation along this contour of the velocity field is constant. This is the circulation theory. And from this, taking infinitesimal contour gamma, infinitesimally small contour gamma, we have the following. Omega omega is vorticity of u. No, we can interpret u as a one form and omega equal du is a two form, and omega at the moment t equals ft minus 1 omega at the moment 0. So vorticity, the vorticity form, or in 3D, it may be understood as vorticity vector, is transformed by the flow itself. So it is conservation of vorticity. No, usually this is derived formally by differentiating the Euler equation, which I did not write. But in fact, this is simply a consequence of right invariance of the metric on our group. Okay, so now I did not say anything about how to substantiate this, how to we have it all on the formal level. So how to make it less formal and give some theorem regarding existence, uniqueness, and so I had to introduce some function classes, regularity classes for this. So let me do it. In fact, it was a great story how this theorem was established, this existence for these equations. It was done first in early 20s by independently Leon Lichtenstein and Nikolai Günther. And in the course of this, they had to create half of today's theory of elliptic equations. So it is one of the key problems to develop today's PDE and analysis. So Lichtenstein.
What names did you say?
Excuse me?
What names you said? I better understand. What names did you say?
It's
Lichtenstein.
Yeah, right.
Ah. Pleasure. Yes. So, let me give a short outline because it is a really remarkable thing. So, consider this equation. No, let me consider the case n equal 2, because it is the same in all dimensions, but here it is a little easier. Then we have the following, let me write down it in the coordinates. F equals F1, F2. This is the map, the flow map. U, x1, x2, t, say u1, u2. U equals f dot f minus 1, u of x. Now, omega is curl u equals du1 dx2 minus du2 dx1. Because it is a two form, I can identify it with a scalar function because it has only one component in this case. And so we have the following equation. First of all, U is incompressible vector field, so du1 dx1 plus du2 dx2 is 0. Divergence is 0. And now it turns out that let us suppose that M is R2. No, we consider velocity fields which go to 0 at infinity and the diffeomorphism which go to identity at infinity, so it doesn't bring any difficulty. And then we can find from these two equations, we can find velocity, restored velocity. So given omega, x1, x2, we can find u, x1, x2 is integral k xy omega y dy, where k xy equals 1 over 2 pi x minus y orthogonal x minus y square. Yes, so this is the kernel. And then instead of this equation, we consider the following equation which are equivalent. df dt t of x dt equals u f t of x. So it is definition of u. Now curl u equals omega xt equals omega 0 ft minus 1 of x. So omega is transported by the flow. And divergence u is 0. So we are given the only thing given omega 0 of x, initial vorticity. Yes, and f0 of x is x. So we start from initial position, which we take as a reference position, and given initial vorticity, and then vorticity by this equation defines velocity. Velocity defines time derivative of position. Position changes, so vorticity is transported, and so we have a closed system of equations which define vorticity. Yeah, so let me write here to be sure that u is curl minus 1 of omega. So our equation now looks d of t dt equals curl minus 1 applied to omega 0 ft minus 1, and all this at the point ft. This is, it can be called vorticity equation. It doesn't have any proper name. Vorticity equation, and this vorticity equation is equivalent to both the Lagrange equation, which were written somewhere here, and initial condition, initial velocity. Instead of initial velocity, I introduce initial vorticity, which is the vorticity of initial velocity. So it is the ordinary differential, first order differential equation on the group of diffeomorphisms. It's a result of reduction. So I use the conservation law which I found before, to reduce from the second order to the first order. Yeah? So this is the first order equation. And the remarkable fact, which was found by Lichtenstein and Günther, is that if we consider diffeomorphisms and vorticities of proper classes, so we consider f C1 alpha. This was the class which was considered by these classics, and omega is Hölder function. No, it can, instead of this, it can be used solvable function, Besse's space. It goes in any reasonable spaces. So we have the D, let us specify 1 alpha. It is a D set of diffeomorphism of these classes, class 1 alpha. And then it turns out that this is an ordinary equation in proper sense. This means that this right-hand side is defined everywhere on the group of diffeomorphism and is a smooth vector field. Right-hand side is a smooth vector field on D1 alpha. So we can use the standard existence uniqueness theorem in ODEs to have this, to have the result that solution exists at least for some moment. Equation or less than some constant. No, what is this time of existence? No, in this theorem is not clear, but definitely it is small time, so that during this time nothing interesting will happen. In fact, Lichtenstein proved much more. I say Lichtenstein because I know his work better than Euler. I think Euler did something isomorphic to this. Lichtenstein proved that the right-hand side is not only smooth but real analytic. Yeah? And his way of proof was quite remarkable, and I think its potential is not exhausted, and we have to find much more in this way. Namely, it turned out that we can consider F not only real diffeomorphisms, but maps, complex maps. This means its domain is the same R2, but the range is some complex neighborhood of R2. And if this map is not in C1 is close to real map, then the right-hand side is defined and is a holomorphic vector field there. Simply it is defined by the same formulas which is written here. Yes? So this means that we can apply the standard theorem of existence and uniqueness for equations with analytic right-hand side. They have analytic solutions. Yes? It is remarkable because the immediate consequence is the following, that trajectories of the particles are analytic lines.
So the analyticity is in both variables, T and S.
Just in T.
Just in T.
No, only in T.
Okay.
In T. Yes, so it is important that in X, and it is not it is some function of some finite regularity, C1 alpha, for example. But in T, it is analytic. Yeah? The direct proof of this, without this consideration, was achieved much later, somewhere in late 80s or 90s, and it required a lot of technical work. Because to prove directly that it is analytic, it should have to estimate all derivatives in time and show that they decrease fast enough and so on. But turned out that we don't need it all. Liechtenstein did it for us, but Liechtenstein did not see it. So he proved that right-hand side is analytic, but he did not write that this means that solution is analytic. Yeah? It is an example of a blind spot which left him without a fine result. The next consequence is, first consequence, trajectories of particles are analytic. Second, so consider a stationary solution. A vector field which does not depend on time. Yeah? No, there is a lot of such stationary solutions. So for stationary flows, the flow lines are analytic. Why I stop on this? Because it has some potential for some further things which I will discuss in the next lecture. What? No, I have more. No, not so weak. Next thing is some other structure. What I want to do here is to show how different structures appear in this problem. It is some other structure. So the problem which I am going to discuss, I'm not going to solve it because I did not solve it, but I'm going to discuss, and it will be touched in some other talks in this conference, is the following. We can consider the different problems for these fluid equations. Now, let me call all of them Euler equations, where we have at least three forms of this. Euler for velocities, Lagrange for diffeomorphisms, and some mixed for vorticity equations. So I will call them Euler equations. We can have the usual initial value problem given f0, f0 dot. F0 and F0 dot. Find Ft. This is the usual initial value problem. Now we can consider two-point problem. Given f at the moment 0 and f1. Find Ft.
Possible.
Sometimes possible, sometimes not. But it is possible to ask this question.
Yeah.
Yes. So, F0 and F1. So this can be called shooting problem. Shooting problem. No, the framework to consider the shooting problem is to exponential map. From F0 dot to F1. No, F0 can be always take identity. So we can start from the reference position. So we give initial velocity field and see where we are at time 1. Yeah? Exponential map. The shooting problem is the same as to find inverse of exponential map, if or partial inverse. Yeah. I have little time to discuss many things about the shooting problem, but the recent advance was the following. We have to, I want to use here the topological method, topological degree to solve this shooting problem. What does it mean? Let us take this identity and suppose that we have the following. So if we take U0 large enough, then suppose that the image is somewhere far away. Yeah? And here is F1. So we have U0 is element of tangent space, of linear space. Yes. X is the map from this Hilbert space to the whole group D, the whole manifold, and we wonder whether this image covers the whole manifold D. Yes. Suppose that we may be sure that for U norm of U large enough, the image is at least far away. Yes, so we have this a priori estimate. No, in usual finite dimensional setup, this is almost all to use the degree theory and to have that the image covers this large domain. Yes? It is well known that in infinite dimensional spaces, degree theory works with a lot of reservations and is restricted to some small classes of continuous maps. And so we have first to study this exponential map from this viewpoint. Yes? And I want to introduce some notions which are pertinent here. Consider first two x, y are, say, one spaces. And we have a map, say, f, x to y. A continuous map. I want to introduce some restrictions of this map, so I have definition. F is called quasi-rule if the following is true. Alright. It can be
In the oil industry, they have something called secondary recovery.
approximated. by rule maps in any ball. I mean, uniformly approximated with very accuracy. So what is rule of maps? So suppose that our x is foliated into x alpha into parallel planes of codimension n. X alpha parallel planes x alpha is n. And x f on x alpha f alpha is an affine map from x alpha to y. And so f alpha depends continuously on alpha in Rn. So then, if we have this situation, then f is called ruled map. If f is not itself ruled, but it can be approximated by ruled maps, then it is called quasi-ruled. Yes?
In the norm topology.
In the non-topology. In the usual topology. And I would restrict even to Hilbert space because there are some irrelevant things, irrelevant difficulties in general bond setup, which I don't like to discuss. Just suppose it's Hilbert space like solar spaces. And no example. The map X Hilbert space Y is R, F X Y, F U norm U square. Yes? This is not a ruled map. No, because it's uniformly curved in all directions. Yes? However, the main example of a ruled map say example X Y, say Sobolev space no, Rn, for example. No, S more than n over 2 to be sure. And consider, excuse me?
Smaller or bigger?
Bigger. S bigger than n over 2. And consider some function.
That means derivatives are in L2. That's what HS means.
Yes, yes, it has S derivative up to the order S in L2. Yes. And suppose that they have function phi. Say C infinity for x in Rn. Then the following map U x going to f of U of x, simplest map, is a quasi-ruled map. Yeah?
What's that?
I'm sorry.
Oh.
Yeah. So this simplest map, just taking superposition with a given function. No, we can. Yes, yes, we can add here x over q, x, and so on. Yes, this is a building block of almost all.
I don't understand the math.
Segment ux go to phi of u.
Oh, you suppose.
Composition with phi.
Okay. Oh,
Yes.
okay.
Now we can add here all differential operator or nonlinear differential operator if they are invertible inverse differential operators. Yes, and we can extend it farther and farther. And we see that practically all operators which are useful in analysis are quasi-ruled operators. For quasi-ruled operators, that, excuse me?
Why?
Because I can write them in some other form, which shows that all such operators are in fact quasi-linear operators. Yes. So let me show it in this example.
So do you need to assume that phi is controlled as derivatives?
Suppose n is 1 on the segment. So phi of u of x, phi u of 0, integral from 0 to x, phi prime u y, u prime y dy. This is the first, so I differentiated and integrated this operator, and now is equal b u of u, where b u v is phi u of 0 plus integral from 0 to x, phi prime of u of y times v prime of y dy. Yeah? So it is a linear operator, no affine operator, depending on u. And now the crucial thing is that if u is even, so here we have v prime of y, yes, and u itself. So we can take u one in just a minute. B u in hs to hs if u in hs minus 1. Yes? And as operator from hs to hs, it depends continuously on u in hs minus 1. Yeah? D u depends continuously on u in hs minus 1, and hence compactly on u in hs. Yes? So, what does it mean? It means that operator of P hs minus 1 compact. Yes? And so we can approximate B u is approximated by B Pn, where Pn functional approximation of, because it's compact embedding, so with compact embedding theory. Okay, and so our approximation is the following. Wait, I'm sorry. It's much better. Fn u is b pn u. Yes. This is approximation when n goes to infinity. It is approximation better and better. So now we can imagine that we can define a category of Hilbert or Banach manifolds such that these transition maps are quasi-ruled. And in this category, we have the morphism quasi-ruled maps between these manifolds. We can, now the group of diffeomorphisms is just a group of this category because the transition maps are defined by some formulas, which means that they are quasi-ruled. And the theorem, which I wanted to formulate at last, is that X is quasi-ruled map. And what I did not say that I introduced frequent quasi-ruled maps for which the usual degree theory can be extended.
What degree theory makes sense?
Is a form. Where the degree theory makes sense, and now this side is settled. We can use, yes please.
Is there a dimension restriction here?
What?
Is there a dimension restriction?
It is, I did it in 2 dimensions for n equal 2. Yes, in 3D there are great difficulties which I think Steve Preston will tell us. But in 2D it is true. But it turns out that it is a small thing. The great thing is to prove the a priori estimate, which shows that for large initial vectors, the image under exponential map is far away. This is to be done. Yeah. Okay, so thank you for today, and now tomorrow and after tomorrow I continue to more specific things. Thank you.
Are there any questions? So two things happen in dimension 2. One, this theorem is true, and also the solvability thing is also in dimension 2.
Yes, in dimension
Both things are in dimension 2.
Yes, it's in dimension. I don't dare to go in dimension 3 because there everything is different.
Yeah, okay.
Yes. You know what is the difference between 2 and 3D? No, difference is like this, that you can pull a bolt by a rope, but it's difficult to push the bolt by the rope. Yeah? So this is what happens in 3D.
3D?
Yeah, in 3D, yes. And 3D is like pushing a ball with a rope. I will.
I mean the rope being the fluid.
A rope is, so to say, fluid. Yeah.
So you can push this with
In
the
one,
rope in dimension 2.
in dimension 2,
Oh,
it
the
is.
hole is split.
No, in dimension 2 it is marginally possible. Yes, in dimension 1 it is okay. In dimension 3 it is transcendental.